This is lecture 27. We're back into chapter 21, and we're picking up here with movement of fluid between compartments. If you take a look now at your lecture outline, you'll notice that off to the left, there's an indication that you should be looking on page 807 here at figure 21.4. And taking a look then at that figure, notice there are a number of different compartments being shown, a number of different places, remember, where fluid is found within the body. And if you look at the top part of the figure, notice we're looking at a capillary, and the arrows are showing blood flow then, the direction of blood flow through the capillary. And number one now, and if you look off to the right, upper right-hand area of the diagram, where it's talking about fluid leaving plasma at the arteriolar ends of capillaries. And of course, the arteriolar end from A&P1 is just the proximal part of a capillary, the beginning part of a capillary. And so let's take a look now in the figure itself at number one. And what's going on here is very similar to what goes on in a glomerulus when glomerular filtrate is formed. So this part of the figure should look very familiar to everyone. And we simply have here then hydrostatic pressure, and more specifically blood pressure, forcing some plasma out of the capillary. And you'll recall then, once the plasma has changed locations, once it's left the capillary, then we now refer to the same fluid as interstitial fluid or tissue fluid. Recall also then we were talking about what's happening in terms of glomeruli and glomerular filtrate. If you now go back to the capillary and follow the arrows going more toward the right now within the capillary, and remember what's happening within a glomerulus and within now a capillary in general is that as we lose some plasma from the capillary, as it's being forced out by hydrostatic pressure, more specifically again by blood pressure, you'll recall, and we won't take the time to go through all the reasons again, but you'll recall that what's happening as the plasma moves through the capillary is that the plasma is becoming hypertonic to the interstitial fluid. And you'll recall then that the interstitial fluid, like the glomerular filtrate that we talked about before, the interstitial fluid then, of course, is becoming hypotonic relative to the plasma. And notice now in figure 21.4, number 2 in the figure itself simply shows that some of the interstitial fluid is drawn back into the capillary by osmosis, by osmotic pressure. And I'll give you a minute then to jot down this information in your notes and to then just take a minute and make sure you're good with what's going on here. So again, number one on the diagram, blood pressure has forced some plasma out of the capillary where it's become interstitial fluid. Number two then, because of a difference in osmotic pressure, because again the interstitial fluid becomes hypotonic and the plasma becomes hypertonic. Number two, now osmosis is drawing some of the fluid back into the capillary. Let's take a look now at number three in the diagram, and notice here we have interstitial fluid entering lymph vessels, entering those very small lymph capillaries that you'll remember from A&P1. But again, just generally, the figure is showing interstitial fluid entering these small lymph vessels. The force here, again, is hydrostatic pressure. So this interstitial fluid, some of it is being pushed into, physically pushed into the small lymph vessels. And now notice when the interstitial fluid has moved into a lymph vessel, we use the name lymph. So again, it's the same fluid as the interstitial fluid, which was essentially the same fluid as was plasma, but we've gone now from using the term plasma to using the term interstitial fluid or tissue fluid, and then to using the term lymph, mainly based on the location of the fluid. And again, I'll give everyone just a minute to jot down what you would like to hear in terms of hydrostatic pressure, not blood pressure now, but interstitial fluid pressure, another form of hydrostatic pressure, another form of fluid pressure. So the interstitial fluid, picture it building up now within those interstitial spaces. And of course, as the interstitial fluid accumulates, it acquires a higher and higher and higher pressure. And again, this higher pressure is high enough to push, to force some of the interstitial fluid into the lymph vessels. We won't bother with the remainder of the figure. And so notice where we're seeing transcellular fluid in the lower left, and where we're seeing an accumulation of cells in the lower right. Notice there's really no net difference here. The arrows are kind of going in both directions. And so again, in terms of net movements, we're looking at the three that we've just talked about. This gets us into section 21.3 on water balance. And notice here now we're looking on page 808 at figure 21.5. And if you look at the two parts of this figure, you'll see that the left part, the A part of the figure, shows major sources of water within the body, which we'll talk about first. But then notice the B part of the diagram is showing different mechanisms by which the body loses water. So, talking first of all about water intake, and you might just want to jot down here from the A part of the figure that total daily water intake is about 2,500 milliliters. And this 2,500 milliliters then would be the equivalent of 2.5 liters if we use different units. So every day on average, we're taking in about 2.5 liters, about 2,500 milliliters of water. And now from the figure, and going back to your lecture outline, just very quickly, notice we have water obtained from drinking then, the major source of water intake, and accounting for about 60% of total intake. Water obtained from food, from moist foods, about 30% of our total intake. And then notice number 3, the so-called water of metabolism, making up about 10% of water intake. And of course, metabolism implies chemical reactions, implies metabolic reactions. And what we're saying here then is that some chemical reactions produce water as one of the products. And here you might want to add to your notes then one example of producing water by chemical reactions, one example of producing water of metabolism is dehydration synthesis reactions. And you'll recall this term from A&P 1, and I would like you to review this and be familiar with it for this part of chapter 21 also. So dehydration synthesis reactions. If you have your book open now, you can flip back to page 124. And if you don't have your book open at the moment, if you've just printed out these figures instead, you can just jot down again. We're going to be looking right now on page 124 at figures 4.1, 4.2, and 4.3. Again, specific examples of dehydration synthesis reactions. And so 4.1 then, top figure on the page, notice what's happening here is that two monosaccharides are joining by a dehydration synthesis reaction to produce a disaccharide. And way off to the right then, the other product of this chemical reaction, in addition to the disaccharide, the other product is water. Another specific example of a dehydration synthesis reaction, figure 4.2. And so again, going left to right, if we assume the reaction is occurring in this direction, we have a molecule of glycerol. 3 fatty acids are joined to this molecule of glycerol, producing a triglyceride, remember, a fat molecule. And in the process, 3 water molecules have also been produced. So again, a dehydration synthesis. Dehydration, taking away from these molecules what's needed to synthesize, to make water. And then finally, figure 4.3. And again, just a reminder from A&P 1, when we join 2 amino acids together, this results in a larger molecule called a dipeptide molecule. And again, notice off to the right, in the process, a water molecule has been formed. So again, another example of a dehydration synthesis reaction. And again, dehydration synthesis reactions then, examples of, back to chapter 21, examples of producing water of metabolism. And we'll stop here.